So, having said this, we are now staying in the finance sector with our next two speakers. Together with Matthias Kaiser, Business Development Manager at Anaqor, and Dr. Daniel Herr, standing here at the right side, Senior Consultant at Define, we are focusing on the benefits from quantum computing. Or more concrete, they will demonstrate an easy and fast way to implement, deploy, test, and monetize quantum applications using the PlanQK platform and present a use case that covers credit card fraud detection. So, you can join me here on stage, and I will use the time to introduce you as well. So, here are three speakers, but it's the two of you, right?
Correct.
Perfect. So, Matthias holds a degree in quantum information technology from the University of Vienna. And in the last years, he has worked in business development and commercialization of deep tech products. And Dr. Daniel Herr holds a PhD on quantum error correction at Riken in Japan. And so, the stage is yours.
Thank you. So we will start. I will tell you a little bit about Planck, and then we will go in a couple of use cases, and then Daniel will go into one specific use case a little bit more in detail. So what we see when people start with quantum projects in their companies, it's often very similar questions they ask themselves. There's, of course, where do I even start? There are different kind of technologies out, different kind of algorithms. It's very hard in the beginning to start this journey and to do the right decisions. Second of all, of course, if it's a company, they have to argue in front of the management why they should spend time and money on quantum computing. So they have to find also some kind of business value, or at least potential business value of the technology to spend time on it. And then, of course, another question is often related also to the first one is hardware or technology centered, which hardware, which algorithms should be used. The good thing is you're not alone. If you have asked yourself this question, there are many companies who have, and there's also the reason why the Planck project was started in 2019, which is a project of many different industry players from Germany and Europe, together with academia, which basically had the idea to come together and try different kind of applications of quantum computers out, test different hardware, different algorithms, and see what works and what doesn't work. That was the idea behind it. By now, it's over 100 different companies and academia players which are part of it. And we will learn a little bit about some of the use cases that were done. For example, Define is also one of the partners of that project. Another question that we ask ourselves during the project is then you have different stakeholders which work together. You have quantum developers, they're usually physicists or mathematicians, which have a very specific skill set. Quantum code is very different to classical code. It is Python, but it's still very difficult because it's gate-based. You have hardware providers, and then you have on the other side, you have the industrial users who are used to very easy-to-use interfaces, REST APIs, so on. So the question was how we can bring them together, that the industrial players don't have to, for just a proof of concept, which it was, to redevelop all of their apps, and on the other side, how we bring then also the quantum developers into that. Here the idea was to build not just Planck as a project, as a community, but also Planck as a platform. And this is what we do at Anaqor. This is our core expertise, is to build the Planck platform, which is exactly doing this, bringing these parts technically together, allowing the quantum developers to put their code into the Planck platform and offer it as a service to as a REST API based service to the industrial users, potential industrial users, and of course also connect different kind of quantum hardware, which is of course also the benefit from the industrial players, that they don't have to concentrate using one specific hardware. They can test out different kind of algorithm, different kind of related hardware. In that project, we tested out over 30 different use cases. Daniel will present in a moment one of them. I will also go through a couple of them, but we will do this only fast. So what's next with Planck, the project? The Planck project is running out end of this year, but we as Anaqor will further develop and also further run the Planck platform. And basically the idea behind it is that a quantum developer, so if you're a quantum developer, you have algorithms, you have code, you can monetize it on our platform. That means you can upload your quantum code. It is put it's made into a service and offered to industrial player who then can consume it and pay per use for the system. And the industrial players, of course, they get presented everything in a form that fits into their existing software portfolio, so they can just plug in the classical part, plug out the classical part, and plug in the quantum part. And of course, have also different kind of hardware related to this. Which brings us also to the learning, so the important points I want to make. The first one is, I think, the most important that we see, because it happens too often, is that companies lock themselves too early into the hardware. There are several reasons for this. The most obvious is nobody knows which is actually the hardware that will survive the next 10 years in quantum computing. We're so early. There's many different implementations of quantum of qubits, but not all of them will stay. So if you lock yourself too early, you might be on the losing side. Second of all is also not every problem can be solved in the efficient way on all quantum computers available. So that might be that you have tried quantum computers, had a bad experience, however, that might be connected to the hardware you chose. So it's always advisable to try different hardware out. Also the same is true for algorithms. Many different algorithms can solve one problem, so try out. And most importantly, I think is also what we do currently here, is learn from your peers, talk with others. There's people around who were at several stages in that journey, and probably you can learn a lot from your peers. I will go now to a couple of cases, but we do this only fast. If you have questions to one of the cases, maybe you see one that is interested to you, I will be circling around outside later, so just stop me and we can have a discussion about this. Quantum chemistry, we heard it already before. We'll just go fast through. This is a case with methylamine that we at Anaqor did. Methylamine is one of the basis for organic synthesis, and to simulate the behavior of that molecule can potentially lower energy needs and make organic synthesis more efficiently. Quantum manufacturing, also many different applications of manufacturing. Here an example of defect detection using quantum machine learning. Quantum power, so power generation and power transport. There's also a case by Define, which we will not hear today, but it's also a very interesting case. You can also stop Daniel later. So logistics, very known case. I will not go in detail. Now we are actually at the part where Daniel will talk about applications in finance of quantum computing.
Yes, exactly. So I will only focus on 1 or 1.5 use cases, which is the fraud detection. And what we looked at is, maybe a quick anecdote. It's been a couple of years. I was out with a couple of friends, and it got quite late. Then I wanted to take a scooter home, tried to scan the QR code, didn't work. Tried to scan it again, it didn't work again. So the problem was my bank declined this transaction because I usually don't buy anything at 3 a.m. in the morning. That is a false positive. So we have some transactions classified as a fraud, which was not a fraud. The opposite is even worse. If a fraud doesn't get classified as a fraud, and then we lose money. So a good model would be very helpful. And that's what we try to tackle here. So we used a couple of data sets, very different types of data, also to test out the model. Generally, the data was, we have a lot of valid transactions and very few fraudulent. So we have a high imbalance. So the model also needs to take care of that. And then we were confronted with the problem, how do we now solve that with a quantum computer? So we eventually decided on a model, and this gave us relatively good results in comparison with classical models. So like some standard models, sometimes it performed better, sometimes it performed a bit worse. So it depended also a bit on the data set. But maybe the spoiler is it takes a very long time to actually run that. So some of you in the audience maybe played around already with these quantum neural networks, tried to do backpropagation and then analytic or the gradient calculation. This takes ages. So our first estimate was like 60 years, which is basically useless. We managed to get it down, so we actually managed to run it on IBM hardware within reasonable time, which was like a week, to just train the model. This is actually in comparison to the classical model that is trained in maybe a matter of seconds. So we still have a bit of a discrepancy here. So these are the results. Maybe a quick overview on what the model looked like. We thought we can use something that is a bit generative in nature. So we settled on a generative adversarial network. And the main idea behind that is we had, I think that was just after these supremacy experiments, or now quantum advantage experiments from the Sycamore chip. And these were good sampling devices. So we thought, okay, NISQ devices are good sampling devices. Maybe we can use that as part of a generative model. The problem is, of course, learning this distribution that you want to sample from. This will take some time. Yeah, we implemented that. We were able to run that on actual hardware, which was nice. And yeah, the big question now is also when we talk to our customers, when a transaction is now classified as an anomaly, why is it an anomaly? So there's a lot of explainability going on, which was also very interesting research because it's at like a friction point between, like, on the one hand, we want quantum algorithms to perform better than classical, so they should not be simulatable that easily. On the other hand, we want to have them explainable. So we did a few investigations in that, also published a paper on that. Maybe coming back to the platform of Planck. So in the end, this was all funded by the German government, and we have now various different use cases, and one of them is this credit card transaction use case. And we wanted to make it very easy for the customers of the platform or for the users of the platform to actually run then their first experiment on the hardware. So we wanted to reduce the barrier a bit. And I put in a screenshot what the platform actually looks like. So you can basically select one of the algorithms. You can select one of those pre-defined data sets just to test it out, and then click run. And it's as easy as that. On the other hand, we also published the code on the platform. So if you were to actually run it with your modifications, like your data set probably needs some adjustments, you can also do that. And yeah, I think that's a good demonstration of the platform.
Yeah, then please, if you have questions, please feel free to.
I would first say thank you. So, are there questions from the audience? Now it's the chance. We wait. Oh yeah, perfect.
Yeah.
I come up. We have that time.
Thank you for the very nice talk. I'm sorry in advance for my very stupid question, but how could quantum computing help to solve such a singular case as the one from your anecdote, buying something at 3 a.m. in the morning?
So actually, we were already quite sure that in terms of speed, the quantum solution would not work. So actually what we were investigating more is how what quality of results do we get? So we looked at F1 scores often and did some area under the recall precision curves. These are basically metrics on how good your models perform on the data set or on the test set. And there we hoped to get like better performance. And then of course you can always put your metric as you want, and then you get better performance. In general, I would say it depends a bit on the problem. So we had some problems where the dynamics of this quantum neural network performed better. In some other cases, it wasn't that good. So it was a bit of a heuristic in a sense. So I would say, and I mean, most of these experiments at the moment are like that. So you don't have now a experiment that definitely outperforms classical computation. We are still waiting for that. But at least here, in some cases, for some problems, we had some advantages. Yeah.
Oh, where? I saw a hand over there. Okay.
Thank you.
You're welcome.
A follow-up. How much better were your F1 scores and your area under the?
I think in this one simulation I showed, it was relatively similar. I think it was like for one data set we had something like 0.89 for the quantum case and 0.85 for the classical case. So it's not that much. Yeah, I mean it's already the existing models are quite good for anomaly detection. Maybe there's a few other things. So the model itself is inherently explainable in a sense. So it's generative, so you can compare like the generated version versus the transaction that you want to compare. But of course, you can also have a generative model purely classically. Maybe for the further use of this, we actually had a project where we implemented this at a customer, but then we only used the classical version. So we had just a classical neural network there.
Okay, further questions? If not, then I have a question. What are your next projects that are planned? Maybe together or alone?
So for us, I think the next project is to commercialize the platform. That's the next big thing that we're currently working on, because the project goes to an end, so it's not financed starting from end of the year. So for us, the important thing is, of course, to get the platform to a point that it's usable for general public. We can already process payments on the platform, so that will go live next year. And it's of course the big project where we also work a lot currently with industrial customers together to make that happen. So this is for us the big next thing, is to commercialize Planck platform.
Yeah. For me personally, I would say, applying for some tenders also to continue tinkering around with the technology, because I think it's, even though now we don't have any examples where it's outperforming at the moment, it's still very interesting, and I still want to continue in this field. Currently we're doing a couple of tenders.
Okay. So Matthias, you said it already that you're working with a lot of customers, and what are the biggest challenges in integrating quantum computing solutions into enterprise infrastructures?
I think it's what I said in the beginning. It's basically that the industrial customers are used to a certain kind of way how they consume software, and often quantum software is not providing that yet. It's mostly algorithm based, and that makes it, of course, very difficult for industrial customers to engage with that in an easy to do way. And I think this is the biggest. And then, of course, the second big thing in the room is at least also, I think, knowledge level. There is still a big gap. Like the expectations are sometimes very high or very low, and it's expectation management. It's also like making people clear that even though the hardware is not ready, it's not that long. It's not that long until it is, and if you want to be part of that game, you should start now because it's it takes a couple of years to integrate new innovation in companies. But this process is it's slow, but it's moving. So we see it moving. This is good, but it's still a lot of work to do for us.
Okay, thank you. I think that's a good final word. Thanks to you again.
Thanks. Yeah.